All right, practice problems. So, if you want, guys, go ahead and see if you can do these questions on your own and then look back to the video. If not, though, then just, yeah, you can follow along with me. So, we've got a pendulum bob. I'm going to draw a little picture here. All right, so there's my pendulum bob. We also, if we do our free body diagram here, we have a FG pointing straight down, right? So that's FG. This FG is going to be made of two parts. It's going to be made of FGY and FGX. The other thing that we can put into our picture here is that this angle in our triangle is also going to be theta. And now we're looking for theta, right? So in this case, we know we can figure out FG easy enough. FG is equal to mg, which is equal to 0.25 kilograms, needs to be in kilograms, times 9.81 meters per second squared. So FG is going to be 2.4525 newtons. And it also tells us that our restoring force is 0.468 newtons. So FGX is going to be 0.468 newtons. Okay, so now that we know the opposite side and we know the hypotenuse, we just got to figure out what theta is. So, right? So it's with the SOHCAHTOA, right? So the SOH part of it. So it looks like we're looking for so opposite and hypotenuse. We need sine. So I'm going to say sine theta is equal to the opposite is FGX, so 0.468 newtons. Over our hypotenuse was 2.4525 newtons. And now I'm just going to go with theta is equal to the inverse of sine of that. Which is 11 degrees. 11.0 degrees. All right, next one. A 0.5 kilogram pendulum is pulled back and released when the height is 0.6 meters above its equilibrium position and its speed is 1.9 meters per second. What is the maximum height of the pendulum? Okay, so what we're going to say is that, well, let's just think about this for a sec. So if we drew, I'll draw another picture. All right, so there's our pendulum swinging, right? At the top of our swing, this would be all EP, right? And that would also be the total energy, E total. At this point down here, that's going to be a combination of EP and EK. So let's make our equation out of this. We're going to say E total is going to be equal to EP plus EK. And I know that the total energy is going to be equal to the potential energy at the top. So that's going to be mgh. And I'll put a little max beside it because it's going to be the max height. That's going to be equal to mg, just the h that it gives us, plus 1/2 mv squared. To make things a little bit easier, we didn't even need this mass. We can cancel all of our masses. Next thing I'm going to do is divide everything by g. So this is going to turn into h max is going to be g times h plus 1/2 v squared all over g. And if you plug in all of that, you guys can do that on your own, you'd end up with 0.78 meters. Okay, moving on to number 3. A 2.6 gram mass experiences an acceleration of 20 meters per second squared at a displacement of 0.7 meters on a spring. What is K for this spring? So I'm going to start off by saying F net is equal to Fs, the restoring force, right? Hooke's law. So F net, Newton's second law, is going to be mass times acceleration. Fs is going to be negative kx. And it's asking us for k, right? And we know all this other stuff. We know the mass, acceleration, and k. So rearranging this, we get ma divided by negative k, or negative out front, doesn't matter, is equal to, oh, sorry, negative x, we'll say, is equal to k. Now I'm going to carry on up here. Our mass is 2 point, oh no, sorry, that has to be in kilograms, so 0.0026 kilograms times, now the negative symbol that we have here, all that's doing is just making sure that whatever I put in for my direction of my acceleration, let's say, so if this was positive, so 20 meters per second squared, it's going to be over. So the direction of my acceleration needs to be the opposite of whatever my x value is. So this would be negative 0.7 meters. And then this is all negative out front. And the only reason why that is because it ends up giving me a positive value for my k. So yeah, it didn't really tell you anything about directions though, so you'd probably be safe on this question just to take the absolute value of it and just kind of ignore our negative symbol there. But either way, it does work. I just wanted to kind of show you that it does work out with the negative symbol as well, if you chose a direction for the acceleration or chose a direction for the displacement. They're just always in opposite directions. Okay, so if you plug that in, you should end up with that for a value of k. All right, last one. Number 4. A mass vibrates at the end of a horizontal spring, gives you the spring constant, along a frictionless surface, reaching a maximum speed of 7 meters per second. If the maximum displacement of the mass is 85 centimeters, what is the mass? So we can start off by saying EP max is going to be equal to EK max. EP max is going to be 1/2 kx squared when x is a maximum, right? That's going to be equal to 1/2 mv squared. Now we can deal with those 1/2s if we want, but the same, we can cancel those. We can just go, okay, well, 1/2 on the top on both of them, so they're gone. And now we're just looking for m. So if we rearrange this, this becomes kx squared divided by v squared is equal to m. And if you plug your numbers into this equation, you should end up with 1.84 kilograms. Okay, so that's going to be it for the practice problems. Go ahead and do the hand in the sun.